Let's solve this problem. A rectangular concrete beam has a simply supported span of 6 meters. The width of the beam is 250 mm and a total depth of 450 mm. And it is reinforced with a total steel area of 1,875 millimeters square. The effective depth is 375 mm. Determine the maximum uniform live load applied for the entire beam. Use FC prime equal to 27.6 megapascal and Fy equal to 414.7 megapascal. So first, we are going to illustrate the problem. So we have here a rectangular beam and it is simply supported beam because it has a simply supported span. So the tension side of the beam is located at the bottom of the beam and the steel area is equal to 108.75 mm square. So the dimension you have 250 mm and for the total depth is equal to 450 mm. The effective depth is what I've said. The effective depth is located at the centroids of the bars. So this is your D and that is equal to 375. mm. Okay, we have 375 mm. Okay, so we have now if that is the D 375, so the cover from the centroids of the bars will be 375 or 450 minus 375, so it is equal to 75 mm. So this is 75 mm. If we draw the strain diagram of the beam, okay, if this is the location of the neutral axis, the strain will varies linearly from the neutral axis to the extreme fiber of the steel bars. Okay, so and also to the steel bars. We let this one as our this is the strain. This is the strain of the steel bars and this is also the strain of the concrete, which is equal to 0.003, and C is from the location of the neutral axis to the extreme fiber of the beam at the completion side. This one, this one will be equal to D minus C. And for the force, the compression force, The equivalent compression force of the concrete will be equal to 0.85. This is 0.85 FC prime times the depth of the compression block. So this is from the centroid, and that is your compression force. Your tensile force you have also here as our T. Okay, so our beam is a simply supported beam. So we assume that this is the illustration of our beam. So this is the weight of the beam, and the span is also equal to, the span is 6 meters. So we have to find the maximum uniform live load. Maximum uniform live load. So this is your WL applied for the entire beam. Okay, we will use FC prime. So our given, so we have to use FC prime. Given FC prime is equal to FC prime is equal to 27.6 megapascal, and our FY is equal to 414.7 megapascal. So first we have to compute the depth of the stress block, the compression stress block. For equilibrium condition, our compression force is equal to the tensile force. So for the compression force, you have 0.85 FC prime times area times B, that is equal to area of steel bars times Fy. So upon substitution, your FC prime is 27.6 and A is unknown. Okay, times B is equal to 250 mm, and the area of steel is equal to 1875. Okay, 1875 and multiply by 414.7. So A, this is the depth of the compression block. So we have 0.85 times 27.6 times 250, that is 5865. 5865. Then 1875 times 414.7, so you have 77562, 77562.5. So your depth of compression block is equal to 132.577. We will use 3 decimal places, 577 mm. So this is the depth of compression block. Okay, this is the depth of compression block. So you have to remember what do you mean by A. Okay, next we need to determine the moment reduction, the moment capacity reduction factor, because we don't know if what will control here in the problem, if it is tension control or it will be transition from compression control to tension control section, or if it is compression control section. So from the previous notes I sent you last time, so I hope you read those notes. Okay, so we have now our depth of compression block. So see the distance from the neutral axis to the extreme fiber of the beam, the compression side, that is C, which is equal to A times beta 1 factor. That is beta 1 factor. Where your beta 1 factor is equal to 0.85 minus 0.05 over 7 times FC prime minus 28. So you have 0.85 divided by 7. FC prime is 27.6 minus 20. So beta 1. So we have to compute. You have 0.85 minus 0.05 divided by 7 times 27.6 minus 28. So that is equal to 0.852. Okay, that is 0.853. Okay, 0.853, and this is greater than 0.85. So use 0.85. So therefore our C is equal to 132.577 divided by 0.85. So you have 132.577 divided by 0.85. So the answer is 155.972. 155.973. Sorry, it is 155.973 mm. So we will check if it is tension controlled or not. Okay, so from the figure, okay, from this figure, C is equal to, okay, we have to get this diagram. Copy. Okay, so this is equal to 155.973. So we have D minus C. Our D is equal to, what is the value of D? 375 mm. So 375 minus 155.973 is equal to 219.0273. 219.0273. Okay, so we assume that the actual steel strain of the steel bars is also equal to the extreme layer of, or the strain of the extreme layer of tensile steel. So this will be equal to EY. So AS is equal to, that is the extreme, the tensile strength, the strain of the extreme layer of tensile steel, that is ET, which is we assume that they are equal to ES. So from here, for similar triangle, ratio and proportion, we can have AC is to C, which is equal to ET is to 219 point, or D minus C. So the strain of the extreme layer of tensile steel is equal to 0.003 times 219.027 divided by C, 155.973. So it is equal to 0.003 times 219.027 divided by 155.973. So that is equal to 0.00421, and this is greater than 0.002 but less than 0.005. You review your notes. I told you, I sent last time the notes for identifying the moment reduction factor. So if you try to check the tensile, the strain of the tensile of the extreme layer of the tensile steel, that is in between 0.002 and 0.005. So you can check that this is within the transition range. So ET is within, or ET is between 0.002 and 0.005. So phi is between, so this is, so this value is between 0.002 and 0.005. So the section will be in transition range so this is either, or this is between compression control section and tension control section. Okay, so we will check also the yield. For the yield strain of the concrete, that is the AY. So this is FY over AS to check if steel yields or not. So AY, you have 414.7 divided by 200,000 megapascal. This is equal to 414.7 divided by 200,000. So that is 0.002 0.074. Okay, and that is less than 0.00421. So since AY is less than 80, so therefore steel yields. So the steel will yield first before the crushing of the concrete. Okay, so next we have the formula and getting the reduction factor since it is in transition zone. So we will use phi is equal to 0.65 plus strain at the strain layer of bars minus 0.002 times 250 divided by 3. So we will use this equation in the analyzing the transition zone section. So I will move this. So equation used analyzing a transition zone section. Okay, so we have this equation. Then we have to substitute the value we have strain of the extreme layer, which is equal to 0.00421. 0.00421 minus 0.002 times 250 divided by 3. So our fee, okay, you have 0.00421 minus 0.002 times 250 divided by 3. Okay, so then you have to add this 0.65. So the answer is 483.834. So that is the value. So the value for the transition zone varies between 0.65 and 0.93, because if P is 0.9, it means tension controlled section. If P is 0.65, that is compression controlled section. So since it is in transition controlled, or it is in transition zone, so it varies, the value of P varies from 0.65 to 0.90. Then, since we already have our Phi, we can determine our moment capacity. Okay, the ultimate moment capacity of the beam. Ultimate moment capacity of the beam. We have the formula mu is equal to Phi mn, where your nominal moment capacity is equal to, okay, so we have to write this way, mn, which is equal to, since you can use also the concrete, the nominal moment capacity for the concrete, which is also equal to the nominal moment capacity of the steel bars. So you can use also this one. We have TS, no? We have TS times D minus A over 2, which is equal to TS Fs D minus A over 2. But since your steel yields, so this will become your F, since Fs, no, is equal to Fy, so you have Es Fy D minus A over 2. So Mn now is equal to 1875 times, that is the area of steel. Your Fy is 414.7. 414.7. Your D is 375, and your A, the depth of the compression block, is equal to 132.577. 132. I have to move this one. 132.577 divided by 2. Again, 132.577 divided by 2. So you have 132.577 divided by 2. So you have 375, okay, times 414.7 times 1875. So you have 240.042 times 10 to the 6. This is Newton mm, or mn is equal to 240.042 times, to kilonewton meter. Thus, your MU is equal to 0.834 times 240.042. So your ultimate moment capacity is equal to 200.195 kilonewton meter. Okay, so let's try. This is your moment capacity of the ultimate moment capacity of the beam. If we take the another solution in getting the nominal moment capacity, we will use the concrete force. We will take moment about Ts. So you have C times D minus A over 2 versus 25 Fc prime A B. Okay, that is your C times D minus A over 2. D minus A over 2. So you have 0.85. Your Fc prime again is equal to Fc prime 27.6. So 27.6 times A is 132.5. 577 times 250 250 times D is 375 minus A over 2. Okay, let's see what is the answer. Okay, you have 375 times 250 times 132.577 is 27.6 times 0.85. So you have 240.042. Okay. Again, I have to check. Minus 132.77 divided by 2 times 250 times 132.577. You have to check from time to time your solution. Okay, so this is 43. So there is a very slight discrepancy of your answer. So this is times 10 to the 6 Newton mm, or mm is 240.43 kilonewton meter. So if you check, you have the same answer for your nominal moment capacity. Okay, for the nominal moment capacity of your beam. So you have your choice, whether you take moment about Ts or take moment about the compression side, which is the C, the compression force. No? So they have the same moment capacity of the beam. Okay, since we are required to determine the maximum live load, so we need to compute the weight of the beam. So weight of the beam, this is 0.25 times, again we have to check again, that is 450. So 0.45 times the specific gravity of concrete, okay, times 9.81. So let's compute again. 0.45 times 0.45 times 2.4 times 9.81, so 2649. So you have 2.649 kilonewton per meter. Then since it is simply supported beam, the maximum moment due to dead load, which is equal to weight of the beam, is 1/8 W. Okay, so your weight of the dead load is equal to weight of the beam. So for the maximum moment for the dead load is just equal to 1/8 WT r squared, where your WT or weight of dead load is equal to weight of the beam times the span is 6 meters. So 6 meters. So MD is equal to 2.649 times 36 divided by 8, 11.921 kilonewton meter. Okay, so from the formula, the ultimate moment capacity of the beam is also equal to 1.2, that is the load factor for the dead load, plus 1.6, the load factor for the live load, ML. So we have 200 for our MU, 200, this is our MU, okay, thus MU is 200.195, 200.195 is equal to, the unit is kilonewton. 195 times 1.2, 11.921 plus 1.6 ml. So the moment due to live load will be 200.195. So let's see again. You have 1.6, 200.195 minus 1.2, 1.2 times 11.921 ml is equal to, so upon solving, the value of ml is equal to 116.181 kilonewton meter. Since the uniform live load is distributed for the entire span of the beam, the formula is equal to ml is equal to 1/8 WL times L squared. Since WL is equal to 116.181 equal to 1/8 times the weight, uniformly distributed weight of the live load, times 6 squared. So WL is equal to 8 times 116.181 divided by 36. Therefore, WL is equal to 8 times 116.181 divided by 36, and the answer is 25.818 kilonewton per meter, and this is the answer. So again, you have to box your final answer, or you have to encircle your final answer. Okay? Thank you.